Hello. So in this video I'm going to estimate or predict the period of oscillation of that mass on the spring that I posted yesterday. I've summarized the data here. I have the extension of the spring in inches, and I subtracted the 2.2 inches with no mass on it. So here's no mass. When I hung those large keys with that mass, 45.2 grams, G is grams, it stretched 11.6 inches. And then when I have the large keys and the hand sanitizer, it stretched 18.6 inches, etc. All right. So I've actually plotted this data. Here's a little picture. Kind of hope you can see it. I do know how to do screen capture, but here we have the data. And actually, contrary to what I said, it really falls very nicely on a straight line. When I did the video yesterday, I thought it wouldn't. But in fact, the first and the third and the fourth point are very close to a straight line, and the second one isn't so good. So I'm actually going to be using the 77.1 grams to do the prediction of K. All right. So I'm going to draw a little symbolic picture here. Here's the roof, and here's the little spring, and there's no mass on the spring. And then when I put a mass M on it, it stretches down by a distance L. Okay? And this M in this case is the 77.1 grams. Okay? So if I draw a diagram for this, a free body diagram, we have mg down and we have KL up. Because Hooke's law is force is K times X, or we'll say now K times L. The force is proportional to the displacement. By the way, Hooke was a contemporary of Newton, who would have been one of the best scientists in his day if it weren't for Newton. So, kind of sad for Hooke. Anyway, all right. So when I plot that data, it's a straight line. That's what Bass is predicting, and K is the slope of that line, the force divided by the distance. So that K is going to be not M, but mg over L, because remember the force is mg. Okay, and in our case, M is the 77.1 grams. And G, and I know I would like to use GM for grams, but the standard is G for grams, so you just have to know by the context. That's gram, and that's acceleration of gravity, which is 981 centimeters per second squared. All right, and I'm dividing this by the length, which is 18.6 inches, but I want to convert that to centimeters. I'm going to multiply that times 2.54 centimeters per inch. So I get K is, all right, well, let's just do it all out. 77.1. I'm not going to use a little star for times because the decimal point is a point. Okay. Times 981 over 18.6 times with the star 2.54. And then what are the units? The centimeters cancel, the inches cancel, and I get 1 over seconds squared. Okay. Oh, I forgot the grams. There's a grams over there, so it's grams per second squared. That's the unit, which I figured it out on the calculator, over here, and I got about 1600, rounded to 3 significant figures, grams per second squared. All right. So that's actually all I need for this. I need from this table. Oh. Except for this is, remember the mass of the hand sanitizer plus the large key. So actually I've estimated K, and now I'm going to estimate omega naught is K over M. So I was surprised by two things after when I analyzed the data from yesterday. One is how nicely these four data points were on a line. And then second is I realized, oh, I neglected the mass of the spring and I should have put it in. Okay? So the mass of the mass we're going to use in omega naught is K over M is going to be the 77.1 grams for the keys and the hand sanitizer, plus the effective mass of the spring, which I talked about in the notes of that video. I figured out the mass of the spring here, and then I halved it because it's not all accelerating as much. So that's 57.3 grams. And that gives me 134 grams. All right. So now I can get rid of that 77.1. All right. So omega naught is square root of K over M. So that is the 1600 grams per second squared divided by 134 grams. Okay. The grams cancel in seconds squared is on the bottom, but it gets square rooted. So I end up with 3.46 second to the minus 1, or 3.46 inverse seconds, or 3.46 radians per second is what it really means. I'll be talking about the equations later. Okay. So you probably hear some other math in the background. I hope it's not too distracting. All right. So what do we got here? So the period is going to be 2 pi over omega naught, which I got as 1.82 seconds. That's predicted. And the measured, when I went to measure it, it was really very close to 17 seconds for 10 oscillations, or 1.7 seconds per oscillation. The period I observed was 1.7 seconds. In fact, when I went and I did actually 50 oscillations, it took 86 seconds. Okay, I actually got 50 oscillations. Sorry, I want to do it the other way around. I want a time. I actually got, 86 seconds, and I actually did 50 oscillations, and that gave me 1.7, that gives 1.72 seconds, and this is observed. Well, that's not too bad. I mean, keeping 3 significant figures we see was maybe a bit much, because they almost agreed to 2 significant figures. So that happens in real life, right? We don't expect everything to be exact. All right. So let me show you again that graph. Here is, again, plotting the mass up here and the length this way. I plotted it this way because remember now the slope is K. Okay, so if I think about, and see there's a data point there at the origin, no force if there's no extension, and 1, 2, 3 measurements I made, and those 4 points are pretty good on a straight line. All right, well, we're going to be talking about differential equations more next time and how this goes, but for now, we've just analyzed this data. And oh yeah, one more thing. I did think about and make an observation of the decay and how long does it take for the amplitude to decrease to about half of the original. It's kind of a hard observation to do compared to measuring the period because you can pause the video to measure the period. But to measure the length, the amplitude is a little bit trickier. I got somewhere between 30, let me see here, I wrote it down. Yeah, somewhere between, where does it go? Somewhere between 30 and 40 oscillations, the period decayed to half. And we observed the amplitude, I said period, amplitude decays to half original amplitude after about 30 to 40 oscillations. Okay, and I could, and that video actually showed 50 oscillations. And another thing that I didn't mention, it's an observation you can do looking at the video, is that the period really did not depend on the amplitude. When the amplitude was big, the period is about 1.7 seconds at the beginning of that experiment. And near the end, when the amplitude was smaller, the period was still about 1.7 seconds. So that's a prediction of the differential equations we'll talk about next time that show that the period of oscillation of a mass on a spring, if it's a Hooke's law spring, does not depend on the amplitude of the oscillation. All right. Well, I'll see you next time. Stay well. Keep engaged. Really, you've got to be watching all these videos. This is our course now, the web work plus these videos, plus you looking around on YouTube, Paul's notes, etc. If you have your book, read the book. Go to Khan Academy. That's what the course is now, right? We're not meeting. I am doing office hours. I'm doing Zoom regularly. Come in on Zoom. Invite me to Zoom. I gave you my cell phone. You can text me, or we can set up a FaceTime if you don't want to do Zoom. But let's keep this moving and let's finish this semester, okay? Stay safe. Bye.